morning. These are not for you. Sorry.
Stop teasing us.
Got a cough there.
So great.
So it has been a hard day's night the last couple of weeks, huh? But we're going to wrap up material in today's lecture. It's going to be relatively light, and at the end maybe we'll have a little time for a touch of review and some questions. And we'll be headed to the weekend. So let's see. When is the exam? Monday. The exam is Monday. So what I'll do, I'll send out an email with the room assignments. It'll probably just be the same room assignments as last time. But if you don't like your room, let me know and I'll find you a new room. I know we had some construction noises. I think that was just bad luck because we haven't had those noises during class, I guess. So that was how it worked out. They decided they were going to tear the building apart on the day of the exam. So hopefully that won't happen this time. Okay, so I said that people can take the exam on Tuesday if they'll be celebrating Easter and they think that will put you at a disadvantage for taking the exam on Monday. And so that said, I do have a relatively sizable chunk of the class that will be taking the exam late, and so it should go without saying, but is anyone to discuss the exam whatsoever with anybody after they've taken it? No. And so I like to have a good time, but I just want to say that concerning this exam with other people taking it later, if I get a whiff of there being any funny business going on whatsoever, trust me, I will be fully behind the roughest sanctions that can basically be applied in that situation. So I typically don't say stuff like that, but with so many people taking it later, I just want us all to be on the same page, and so I might even have something on the exam for you to sign saying that you kind of understand how this works and you understand that if you did something wrong that you will be susceptible to that, which you already know, right, because we're all students here and we know the honor code. Okay, that's all the scary talk, sorry. So office hours, we're going to have office hours today, 12:30 to 1:30. Now, the good news is that we have office hours. The bad news is I got booted out of my room for today. So this is how this is going to work. I'm going to hold my office hour from 12:30 to 1:30. It's going to be in my office. That's small. And so basically, the way that I'd like to go about office hours today is you got to keep the turnover, right? So no one's going to have time to come in and work through things for 5 or 10 minutes. I'm assuming there's going to be a bit of a line. And so this is going to be for some last-minute topical questions, just some clarifications on material. So, of course, everyone is welcome to stop by my office, but just understand there will probably be a little bit of a line, and we just got to keep that line revolving. So, a heads up for that. Workshop. So the workshop was initially scheduled for 1 to 3. So my mother is coming into town this weekend to I don't know. We don't celebrate Easter, but I don't know. We always celebrate Easter, even. Yeah, it's weird. But anyway, she's coming into town, so what do people think about moving the workshop back a little in the day to maybe like 3 to 5 instead of 1 to 3?
Yes.
I don't see a lot of people arguing. Okay, so I'll send out an email reminder, but what I'm going to do is that gives me a chance to maybe have lunch with my mom on Sunday before she heads back out of town. And so then we'll just assemble here, I guess, at 3 o'clock. Shouldn't be an issue. I'll make sure we have the room. Last but not least, so like I said, my mother will be in town, and so I'm going to want to spend a lot of time with her. And so I'm sure you're still going to have some questions via email, and so I'll do my best to get to everybody's emails, but it's going to make it a lot easier on me if you're asking short, topical type questions that I can answer on my phone, right? Because I'm probably not going to be sitting at my computer a ton this weekend. So as always, you're welcome to send me questions, but try to make them such that I can answer pretty easily, right? That's going to make my life a bit easier. Okay, anybody got questions about stuff? All right. So let's get rolling. We were talking about ozonolysis last time. Let's see. That was the 23rd. I don't remember where we were. Let's see. So we just talked about the mechanism. And so the mechanism in ozonolysis, it's a concerted mechanism. We're going to form two new CO double bonds at the same, or single bonds at least initially in the mechanism here at the same time. And so it must be a syn addition because it's concerted. And so after we get to this intermediate, some stuff happens, some rearrangements, a couple of different things, but it's well beyond the scope of this class. And so what we just want to kind of know is that once we form this first intermediate, these other things happen, and so we can do a workup, and so our workup step will push us to our final product, which ultimately is just going to be cleavage of our CC bond. Notice, all right, so this is important. So we've said before that if we have an alkene, basically we're going to end up with two products, right? So we're going to have our top side product and our bottom side product. Basically the different sides of the alkene will form two different products. But is that what we see in this cyclic example down here? Yeah, we're only forming one product, right? And so since we're cleaving the double bond, the carbon 2 and 6, well, they are becoming disconnected, but keep in mind they're still connected through the other part of the ring, right? 2, 3, 4, 5. And so what we end up with in this case is just one product. So don't be confused. I think there might be a sapling question that has a cyclic ozonolysis type question. Yeah.
If there's a ring, will it always be one product?
If there's one double bond. We haven't really talked about the ozonolysis of multiple bonds, but you could imagine a situation where you have a diene, and so let's say you have a double bond also between 4 and 5, and so if you did ozonolysis, you'd cut both and end up with two products, right? But we didn't really look at that case, so I would agree.
The hydrogen that's on carbon 6,
yeah,
that was already there previously.
Right. Yeah, and so here we've got an implied hydrogen, and so knowing that we're doing a reductive workup, we leave everything the same. If we had an oxidative workup, what would have happened to this hydrogen? Yeah, it would have been converted to an OH, so we would have ended up with a carboxylic acid functionality there. Okay, so let's go ahead and add that, I think, to our list. I think we've got all the info we need. So we'll call this reaction, I think is it A? Yeah, it is A, okay. And so we can't really just put it in nice and neat as electrophile nucleophile because we're cleaving this thing. Oh, I did put that myself. Okay, so what we've got is basically we're just going to draw the reaction scheme. And so we know that if we had some alkene that looks like this, we're going to undergo ozonolysis to give ourselves two products. And in this case, they're the same product, but we're going to make twice as much of it. So the reagents, is this undergoing a reductive or an oxidative workup? This is reductive, and so our reagents here, we'll say it's our reductive workup, and so that's dimethyl sulfide. What about, so do you think we can give regiochem or stereochem to this thing? No. No, this one's kind of an oddball. So we'll just say none and none. We know mechanistically that the first step goes through a syn addition, but the ultimate products don't have stereochemistry, so there's nothing to talk about there. So ultimately we've got concerted mechanism. So I guess in addition to that, we could undergo an oxidative workup. So the only difference, of course, is that our implied hydrogens are now converted to OH groups. So that reaction, again, we start with ozone. We hook our ozonator into our reaction. So then we work that up with hydrogen peroxide. I think I just said hydrogen peroxide. All right, so that's table 8. You see a little bit of difference based on which workup we do.
Is everything else the same?
Everything else is the same, yeah.
Does it matter which side you do the double bond on?
How do you mean?
Like, you have it on the left, on the top one, and the right.
Oh, no, not at all. Not at all. Okay, so that leads us to our last reaction. Yeah, we're there. All right, yeah, Lydia, before we do that. straightforward. So it's another concerted mechanism. So we are going to refer to it as a reduction. Alright, so our reduction, here's how it works. It's going to be a reduction with H2 gas, and some of you have probably seen this on SAT when you had a reaction with H2 gas and some sort of metal catalyst. And so that's exactly what we've got. So we're going to have H2 gas associated with some, or at least also with a metal catalyst, and so we're going to undergo reduction. And so our metal catalyst, so you'll see catalysts like this. So you'll see a PT, what's that? What's PT? It's platinum. So you'll have a platinum catalyst in there. You can have a nickel catalyst. You'll also, a very, very common one is called palladium on carbon. And so what it is it's a mixture of just atomic carbon with palladium, and so it gives you a nice, neat solid. It's a black solid, which you might expect it being carbon. And so it's very, very commonly used in synthetic chemistry. So it's called palladium on carbon. So you write it PD and then C. All right, so when we do this, what we'll have, let's start with this starting material. So what we're going to do is we're going to react that with H2. Which number do you want to use here?
Palladium on carbon.
Palladium on carbon. That's probably the one you would use in lab. So you use palladium on carbon. And so what you end up getting is this stereocenter, of course, will stay the same. All right, so it's a concerted mechanism. So are we going to add things to the same side or opposite sides? The same side. So let's add to the front face first. So we'll push our methyl back. The thing that we add to the front is going to be a hydrogen on top. And on bottom, it is also going to be a hydrogen. And so when we say a reduction is basically we're going to add hydrogens and go from a double bond to a single bond. It's a way for us to go from the cycloalkene or just the alkene to the alkane, right? And so we can basically clean the double bond at this point. Of course, there's still going to be a hydrogen there, but the point is we've added here, and this addition is going to be syn. All right, so of course we can add that. We can also add from the back face, and so this stereocenter stays the same. Now our methyl will be pushed forward. We'll add in a couple of hydrogens back like that. So what's the relationship between these two? Yeah, these are diastereomers. All right. So that's reduction. It's relatively straightforward. All right, so we're going to look through a mechanism here. We can't draw a really nice, neat arrow pushing mechanism for reduction because we're having transition metals involved, and they don't always follow our nice organic arrow pushing. So this is kind of, I just want to show you why we get the syn addition that we do. All right, so let's go ahead. This, we'll put PT. And so down here, what we've got is, we're just going to say this is some metal. All right, so here's our piece of metal floating around in there. It's platinum. And so what we're going to have mixed in with that is hydrogen gas. And so the first thing that happens is basically the metal and the hydrogen gas are going to react such that it separates the hydrogens apart. So what we end up with is going to be now our piece of platinum. It's more or less going to look like this. So our hydrogen has separated, and now it's kind of clinging onto the metal, right? They're not bonded together. Now they're going to be bonded to the metal. And just remember, metal, this is metal stuff. This is outside the scope of our class. All right, so of course what we can have is, once we've got this metal hydride complex, we can go ahead and, what I'm going to do is I'm just going to say we've got, all right, we'll just number these. It doesn't matter what the groups are, so we'll say 1, 2, 3, and 4, like this. And so what's going to happen is basically this is our planar alkene is going to approach the surface of our metal, which is bound with hydrogen. And so the carbon and one of the hydrogens will more or less kind of switch places. And so what we end up with is going to be a picture. So now we've got a hydrogen there, but where one of the hydrogen was, we're going to bind our carbon. And so since our carbon is being attacked from the bottom face, our substituents on the left carbon get pushed up. And so the hydrogen that was initially connected to the metal is now on the bottom face, and so the other constituents have also been pushed up. Alright, so you go through this type of intermediate where one of the hydrogens has jumped onto the double bond and the carbon on the left has basically replaced it. And so then finally, what we'll have is this hydrogen, or this hydride right here, is going to jump onto this carbon, and it's going to be a syn addition. Since we've got one face that's facing the metal catalyst, it's always going to be the same face of our alkene that is interacting with our metal catalyst and the hydrogen. And so what we end up with is going to be a structure that looks like this. And so you can see how those hydrogens come in from in a syn orientation. Yeah, absolutely. And so because only one side of the alkene is going to interact with the metal catalyst, we're going to have the hydrogens add in a syn fashion, and so we call it an inserted mechanism. All right, so these have been added syn to the same side of our double bond. So all the substituents are pushed up in the same direction. All right, so that's why we see syn orientation, and of course we could also have flipped our alkene over, right? And so we would say we could also add from the top face. So in that case, our substituents, let's see, they ultimately just need to be flipped here. So what should the relationship be between these two? They should be enantiomers, right? Because if we add from one face versus the other half versus the other face in a syn addition, we get we switch the stereo centers, right? And so what we end up with is we would end up with something that looks like this. So you can see hold on. You can see that we have flipped these stereo centers, and so now what we've got are basically enantiomers, right? Everybody happy with that? It's everything we've been doing all along, right? We start with an alkene, we snap to a face, and we end up having both two possibilities for stereochemistry, and so we see enantiomers here. Okay. That's it. We'll just call that 9. Alright, so what are we adding as the electrophile? H. What are we adding as the nucleophile? H. They end up as H's, right? And so we'll just call it, we add H to one side, we add H to the other side. So our reagents that we'll see, we're always going to have H2 gas. We have to have a source of hydrogen, so it's going to be H2 gas along with platinum, nickel, or palladium on carbon. There's going to be no regiochemistry because we're adding the same group, but what about stereochemistry? Yeah, very importantly, this is always going to be a syn addition of our hydrogens. So that's because we go through it's not technically concerted, but again, these mechanisms are a little different to classic organic mechanisms. So we can call it concerted and still be happy with it. All right, so let's see. Experimentally, how do we do this? So hydrogen gas is kind of scary to work with because it's explosive, right? And so how you do this in lab is typically you'll take a balloon. So we have our hydrogen balloons that we've blown up, I guess a lot more in Chem 103, but we've done it a little bit here. And so what you do is you have your hydrogen gas full of balloon, and so you'll wrap it tight around the needle, and you'll stick it in your reaction, and so basically that hydrogen gas will now pump its way in. And so you can flush out your flask a few times over and over again, flushing out all the air and putting hydrogen in place, and so that's how experimentally this thing is typically done. All right, that's all, folks. All right, and so yeah, Emily.
When we call anything a reduction, is there something that's specific that's happening that happens in all reductions?
Yeah, so one thing that you see in pretty much just about every reduction is the addition of hydrogen. So when we say oxidation, typically it is the addition of an oxygen. When we say reduction, it's typically the addition of a hydrogen. That's one key definition between oxidation and reduction. Yeah. All right, so that's it. That's 9 reactions, and so honestly, I know it has been a hard day's night the last couple of weeks, but it doesn't get much harder than this. This is, I mean, you guys have made it through this chapter of organic chemistry, so well done. It might be similar difficulty the rest of the way, but this last 2 weeks have been, I mean, it's a little tough learning all these things, so well done. Keep up the good work. We've got the exam on Monday. I figured we'd spend the rest of the time maybe just looking over some nuances of doing these types of reactions, and I can also, you know, take plenty of questions. So one thing I did want to add is that if we have something that looks like this, so let's say, I don't know, what reaction we're going to do. Let's say we're going to do H2 with palladium on carbon. So we know that's going to be a reduction. So pretty easily we can just think of a reduction as a removal of the double bond, right? We're going to convert the double bond to a single bond. We're done. This would be the product. But you might also see some cases where you saw maybe this molecule. What's this molecule? This is benzene. Benzene is a really special molecule, and let's talk about why that is. So if we try this, if we try to react this with hydrogen gas and palladium on carbon, what do you think happens? Nothing. No reaction occurs. And so what that tells us is that there might be a little bit of a difference between the double bonds in benzene and your standard alkene. And so you're going to, you know, I think it's chapter 20 that you start talking about the reactivity of benzene and aromatic compounds like benzene. But basically, whenever we have alternating single and double bonds in a ring, and furthermore, when the number of pi bonds involved are 2, 6, 10, not the number of pi bonds, but the number of pi bonding electrons, what we end up out of these two cases is that the structure is incredibly stable. And it's very much just a quantum mechanics sort of thing, because you can ask, well, what's so special about 2, 6, 10, 14? It's math stuff, right? When we talk about electrons, the reality is we understand electrons mathematically, and so when we have 6 pi bonding electrons in a single double orientation around a ring, we call it, like I said, aromaticity. And so because those double bonds are so stable, basically they're not going to react the same way as the typical alkene, because they're way, way, way down here in stability where your typical alkene is up here. And so for these benzene double bonds to react, they have a much bigger hill to climb energetically to get over that, that activation energy. And so what we see is that if we treat both with hydrogen gas and a metal catalyst, we will see this one react because it doesn't, because it doesn't have that single double alternating bond, but here we do, and so we just see no change. So for example, if you, like on sapling, were to see a homework question, it looks like this. How many reactive double bonds do we actually have here?
One.
We just have one. This is the only.
Is that it? Really? Okay. Damn it.
I've gotten a few emails about that one. Wanted to clear that off. All right, so it's just it's aromaticity. You're going to learn about that down the road. Interestingly enough, and again, I can't give you a good reason right now in Chem 206, but when we have alternating single double bonds, and the numbers are 4, 8, 12, 16, it's the opposite. Those are incredibly unstable rings. And so they more or less, it's weird, but you'll learn more about it pretty much in Orgo 2. So that's a quick look into aromaticity, I guess. Okay, let's see. What else we want to talk about? Let's talk a little bit more about, yeah, Cynthia. Yeah, and so this isn't something you need to know whatsoever for the exam. All you need to know is really for the sapling that these won't react while this will the stability. See, right, when we count this, we've got 2, 4, 6 pi bonding electrons, right? And so that fits our criteria for aromaticity. There's another case that we call anti-aromaticity, and so that's basically the even numbers between the ones I'm showing. And so when the number of pi bonding electrons are those numbers, it's actually really unstable. And it's just very much a mathematical quantum mechanics sort of artifact. Yeah. All right. So I've had some questions about, our syn and anti addition stuff in acyclic compounds, and I just wanted to maybe draw out a nice clean picture of how we can think about this. So let's say we have a starting material. I'm just going to go ahead and tell you that the odds of me asking you to give me a starting alkene, which would give us the correct stereochemistry in a given product, it's high. It's pretty likely. I mean, the exam's written, so right? I know what's on the exam. That's a hint, I guess. And so there's 2 cases. When we add an electrophile-nucleophile combo, we've learned about syn stereochemistry, and we've learned about anti-stereochemistry. And so if we want to add these things syn, all right, so if we add them syn, we're going to have electrophile, nucleophile, and so we're going to approach from the top face. And so what we'd end up with is our electrophile would be on the same side. So we've got methyl down. Basically, it's pushing the substituents down, right? And so the nucleophile, right after the addition, is it going to be at the same side of the electrophile or the opposite side? Same. Definitely the same side. And so likewise, the methyl and the hydrogen have been pushed down. All right, so we're pushing down this way when we add our syn addition. And then we've got the alternative possibility. We could be going through an anti-type addition. And so we have electrophile nucleophile, and we'll say anti. And so again, we'll initially attack from the top face. So we end up with the stereocenter on the left the exact same. But when we show our newly formed carbon nucleophile bond, assuming that this is right after the connection has taken place, is it going to be on the same side or the opposite side as the electrophile? It's going to be on the opposite side, and so that means that the substituents on the left side, in our blue case, are getting pushed down. But what's happening to the substituents on the right? They're getting pushed up now. And so what we see is that we have methyl pushed up, and the hydrogen pushed up. And so when we compare products A, let's do that in blue, we have product A and we have product B. Are those the same molecule? They're not, right? And so you can see that. Let's do a little bond rotation. And so let's rotate this product B so that the electrophile and the nucleophile are on opposite sides, like in product A. So if we do so, we'll keep our left carbon in place. But we will flip our nucleophile down, all right? So we're going to rotate that 180 degrees, and so that means we'll have a wedge up here and a dash up here. And so what's going to be on a dash? It should be hydrogen, right? Because the dash going up is 180 degrees from the wedge going down in the picture above. And so we're going to have hydrogen there and methyl there. And so now when we compare these things directly with our electrophile and our nucleophile in the same place, are they the same molecule? Definitely not, right? We have this right stereocenter that has been flipped. So this is the point, is depending on the type of mechanism, whether or not it's syn or anti, we're going to end up with 2 different possible stereochemical outcomes. And so just like when we think about the addition of an electrophile and a nucleophile to this, right, we say, oh, we're going to push those things down. If we want to go the other direction, right, if I give you a product and I say, all right, what does the starting material look like? Well, instead of pushing the things down, just push them back up, right? Just push them back up so that they're going to be this picture that I'm showing you right here. And so likewise, if we know that we went through an anti-addition, well, instead of pushing this one down and this one up, just do the opposite over here. Push these back up. They had been pushed down, and push these down, such that we end up with the original picture. And so the original picture, or the picture that we end up with, is the double bond. That has to be the double bond, right? That's going to lead us basically to those products. All right, so again, what are the chances that you're going to see something like that?
100%.
It is 100%. I'll just tell you, it's 100%. So definitely be comfortable with that material. All right. A few other things. Let's see. Let's say we had a compound that looks like this. Okay, so how many labels can we give to this to give us some stereochemical information? All right, so let's think about it. So, do we have the chiral center? Yeah, absolutely, we have the chiral center. And so to figure out what our label would be for this chiral center, we know we have a hydrogen there, and so we would prioritize 1, 2, 3, 4. Is that R or S? All right, I hear both. So let's put our thumb backwards. We can do it with our right hand. Can we curl 1, 2, 3? Yes. Absolutely. So it's definitely R. And so can we assign this a stereochemical label?
No.
Well, do we have different groups off of each side? Yeah, so we can give it a label, right? We could say this is higher priority than this. So this is going to be higher priority than our hydrogen over here. And so would that be an E or a Z double bond? Yeah, that would be E because our higher priority groups are on opposite sides. So can we ever have the Z double bond in the ring there? We can't. And so while we can give it a label, it doesn't mean that the other stereoisomer can exist, right? We do have basically enough information to assign this E, but we can never have the trans double bond in a 6-membered ring, and so this will always have to exist as the E. What about this double bond? Can we assign it a label? Yes. Sure. What would it be?
E.
It would be E, right? Because it's essentially just a trans double bond. And so then the last one, can we assign this a stereochemical label?
No.
Why not?
They're both hydrogens.
They're both hydrogens, right? So we have too much symmetry. We can't assign a higher priority group. And so we have 4 double bonds. I'm sorry, we have 3 double bonds. We can assign 2 labels, but how many of those double bonds can we consider able to switch and give another stereoisomer? Yeah, it's just the one. So this one, the other stereoisomer can exist. And what about the chiral center? Could we have the S chiral center? Yeah, and so we've got basically 3 stereo sites that we can assign labels to, but how many different stereoisomers can actually exist? 2 to the 2, right? Because there's only 2 that geometrically can switch, right? Because the one in the ring is pretty much stuck that way. And so that limits half of our stereoisomers. So it would have been 8, right? It would have been 2 to the 3rd, but all of those basically Z stereoisomers here, they can't exist, and so that gets cut in half. We just say it's 2 to the 2nd, and so we end up with 4 possible. Okay, just wanted to bring that to your attention. Okay, yep.
Even though that's not a wedge, you would still consider that the 2 to 2.
You're talking about this one?
Yeah.
So we do consider it, right? Because we could have the S stereo center. So we've got 2 possibilities. We can switch this one, and we can switch this one. But we can't switch this one, right? So what we've got is we've got the ability to have 2 out of this and 2 out of this, and so 2 to the 2 is 4.
Because on the forward, you said that you shouldn't switch what's all the way even on a wedge. So,
Well, it is going to depend on the type of question. If I ask you how many possible stereoisomers there would be, I mean, you have to include this one along with the other possible ones. Yeah.
You had a question on both practice exams. It was like which the following alkanes undergoes the least exothermic reaction with like pH and ammonium. How do you tell it which is the
We didn't cover it. Those aren't my practice exams.
Oh.
Yeah, I didn't write those. Yeah. Yeah, Steve.
Can we talk about naming so that compound you just drew on the board? Talk about naming that.
We wouldn't have to name this because this is a more complex example where we have a cycloalkene and then an alkenyl substituent on the, right? So it's more complex than we'd ever look at. Yeah. Rhea?
So here you say we have 3
let's talk about that terminology for a second. How many stereocenters do we have on this molecule?
4.
All right, so let's make sure we understand our terminology. A stereocenter is the same thing as a chiral center. How many stereocenters do we have? We have one stereocenter. We have one chiral center. What you'll also see used sometimes is the idea of stereosites. So a stereosite is anywhere you can give an RS or easy label. So, is a stereocenter included in the definition of stereosites? Yeah, right, that's just a chiral center because basically we add up where we have chiral centers and where we have double bonds with stereochemistry to give us the total number of stereosites. But are all stereosites what we consider stereocenters? No, stereocenters are always just chiral centers. Yeah.
Do you not include trans-cis areas, like for 6-2 groups?
So we did cover that a little bit at the beginning, and so just as a reminder, the reason that we have to use cis-trans, because we only talked about 3. We really only focused on 2 types of stereochemistry, but we also have cis-trans ring stereochemistry. And so what happens is we can have a molecule that looks like this. And so do we have any chiral centers in this molecule? No. Do we have any double bonds? Right, and so we look at that and say, all right, we haven't really talked about how this could have a stereoisomer, but of course, we can also have this molecule. And so are those the same thing?
No.
No, are they connected the same way?
Yes.
Do they have the same connectivity?
Yes.
Yeah, but are they oriented the same way in space? No, and so this is basically that other third type of stereochemistry that we haven't talked about much. And so basically, in addition to double bonds using cis and trans, you can also call this cis and this trans. And you would have to actually name this thing with full specificity in terms of how things work. But we didn't talk much about it really. And it's really the easiest case, I think, of stereochemistry. Yeah.
So just to clarify, if you were given that, going back that molecule up there, and you were to ask how many stereocenters, that would be 1, but stereocenter is 3.
Yes, we would say that there's one stereocenter because we see one chiral center, and we'd say there are 3 stereosites because basically we can assign that many labels. All right. A few more things. Let's see. Yeah.
So if you wanted to draw the stereoisomers of that molecule there, cyclohydrogen, how does it change these to Z?
So to show the Z, so we'll keep everything the same. So then what we'll do is we'll just go the other way, right? And so by going the other way, we have that double bond. And so when we prioritize, we would say that we've got, let's see, we have 1, 2, and then 1, 2. And that's B. How about that?
Yeah, I was about to say. The only way you can do it is if you pushed it inwards and made it like an N shape, I guess. That's the only way I can think of.
Like if you flip the L part downwards, you turn into C then?
Yeah, no, you're right. I totally did that wrong. Okay. I was like, uh-oh. Alright. They pay me to do this too. Alright, so really, alright, we've got to do this.
There we go.
There we go. Alright. You guys are better at this than I am. Alright, so we've got 1, our hydrogen 2, 1 and 2. And so is that E or Z?
Z.
That is Z. Oh man, there's nothing more than the scene feeling when you have a PhD in something and you're standing in front of 150 people and you're
You're like, oh shit.
so it doesn't, these are different molecules. And so we're not undergoing a bond rotation, we're actually just showing 2 different molecules. Yeah, these would never interconvert with each other. Yeah.
In
So you're talking, why don't we call this syn anti?
Yeah.
So we've only been using syn anti when we've talked about basically stereoselectivity of a reaction. And so here, when we're using actually showing stereochemistry, just like we could have a cis-trans double bond, we have a cis-trans relationship here. Syn and anti is basically the stereochemical implication of a mechanism. And so that's when we add things on the same side or we add them on opposite sides. So basically syn anti it's the adding of things. You know, it's the orientation of when we add things, anti or syn. This is just stereochemistry, how they are hanging out, more or less.
Sin would make cis rings.
So let's see. Yeah, I know what you're getting at. Let's draw that out. So absolutely, if we had a double bond that looked like this, and so we wanted to do an osmium tetroxide reaction, which of course must be worked up with water. All right, so is this syn or anti? It's a syn mechanism, and so what we're going to end up with is we're going to have hydroxyl here and hydroxyl here. And so it's a syn addition that leads to the cis product. And so likewise, if we had the alternative, so we could do a bromination with Br2. And so if we do a bromination, are we going to have syn or anti? Yeah, we're going to do an anti-addition, and so that's mechanistically how these things will add. And so what we end up with over here will be trans products, right? And so basically, the syn-anti label is for mechanistically how do they add, and then the cis-trans label is for, you know, how are the products oriented afterwards. Okay. A few more things. Let's see. Let's compare carbocations.
Yay.
This is what I did over breakfast this morning. I sat here and just tried to take this. All right. Which is more stable?
The second one. Wait. Second one.
No, the first one.
Ooh, even more interestingly, let's do this. Let's say, which is more stable?
There we go. It's the right one.
All right, so we've got a primary versus a secondary. So I hear a lot of secondaries, but keep in mind.
I thought.
Uh-oh.
Resonance?
Uh-oh. Okay, so for the primary carbocation, can we show a resonance structure? Yeah, and so a delocalized carbocation versus a secondary carbocation, which is always more stable?
Delocalized.
Delocalized. And so remember, always look for possible resonance. So here's an example where we have what we would call an allyl cation. And so the allyl cation is really stable because it basically, that positive charge is delocalized over two primary carbons, which is just about going to win out. However, is this carbocation closed shell on the left? No, it's not, right? It's always open shell. We can never close. So what about if we had something that looked like this versus something that looks like this? Which is the more stable carbocation? Yeah, so we know we can draw a resonance structure now that will be open shell or closed shell? It'll be closed shell, right? And so now we have this structure. And so because the one on the right is closed shell, that will, of course, be more stable than the carbocation that does have resonance stabilization, but it never has a closed shell resonance structure that we can draw. So keep that in mind. Okay, I got more. Let's see. So, if we had to assign a partial positive and a partial negative to this alkene, what do you want to give to the top carbon?
Positive.
Yeah, which would be the more stable carbocation?
Tertiary.
It'd be the tertiary one, right? So this gets a partial positive, this gets a partial negative. And so when we line up our electrophile nucleophiles, is the electrophile going to line up with the partial positive or the partial negative? Does the electrophile have a partial positive or a partial negative itself?
Negative, God damn it. Negative.
I'm still here, bro. All right, so whenever we draw, let's think about this. If we start our arrow pushing mechanism at this double bond, where do we always draw it to? The nucleophile or the electrophile? The electrophile. So what's electrons going to be more attracted to? A positive charge or a negative charge?
Positive.
And so if we're drawing them to the electrophile, do you think the electrophile is partial positive or negative?
Positive.
Definitely partial positive. All right, so in a concerted mechanism, we do this, and so that explains the regiochemistry. We always want to make sure that we line up our reactant, and in most cases we see Markovnikov type additions, and so nothing really changes too much, but that's why even in the concerted mechanism where there's no carbocation, no halonium forming, we still see this exact kind of regioselectivity. Let's do one more. All right, so let's do an acid. Let's pretend we just did an acid catalyzed hydration, and so we've gotten to this product. Are we done?
Nope.
What do we got to do? We have to deprotonate, right? So we could have another molecule of water in there, or you could just use a generic base or a B, symbolizing a generic base. And so we always think, all right, we want to snap our electrons to our positive charge, but can we do that in this case? We can't do this in this case. Someone is going to do this on Monday. Someone is going to say, well, we can make this neutral by, I guess, adding our oxygen here to this other oxygen, but that, of course, would violate the octet rule. And so what we've got to do in place is we've got to plug off the proton so that the sigma bonding electrons involved in the OH bond can snap back to the OH. And so that is how we get to a neutral product. Any last questions?
You have H3O plus.
Yes. Yeah, and so what you just want to think of is individually for each atom, how many electrons does the neutral atom have? And so in this case, so oxygen is in column 1, 2, 3, 4, 5, 6, and so that's 6 valence electrons. And so we can see here what we do is we count each lone pair electron as 1, and we count each bond as 1. So what we've got is 1, 2, 3, 4, 5 electrons. So we've got one less electron in this neutral atom. Point out to this side. Please. You're talking about up here? Yeah. And so what you can do, try drawing out resonance structures using cell carbons and see basically what those structures are. All right, I'll talk 12:30 to 1:30.
And you'll send out an email about